Now, dear student, chapter number 10, Mechanical Properties of Fluids. And today we have the topic for the discussion here, that is uh, Torricellis laws of efflux, and it is one of the basic practical application of the Bernoulli's principle. And in the previous lecture already we have discussed the concept of the Bernoulli principle, that pressure energy, kinetic energy and the potential energy per unit volume for a non-viscous streamlined flow of a liquid is constant. So what Torricelli's law execute, and the word, special word which we got here, that is called the efflux. Efflux means is simply the outflow of a liquid through a orifice. And what does mean of the orifice? It's simply a hole in a surface from the from edge at a height h from the surface. Okay, so Torricelli law state that as the outflow of a liquid, or the velocity of a liquid, is equal to similar to the velocity of an free falling object which towards the surface of the earth, that is called the v is equal to under root 2gh, as we have opened the container surface to the atmosphere where the pressure is p is equal to pa is there. Okay, so how can we make the assumption by the help of a diagram? So I am just showing you in front of you. Now here I am just showing you a basic conceptual diagram in which we have the container, and initially we are just assuming this container is bound from the top. Okay. Now we have the one of the opening, or the orifice, which is at a height of y1 from the surface of the earth, and here we are just assuming or applying the Bernoulli principle at a point 1. So here I have assumed that point number 1, and the another point which is the surface of the container where the we have the flat surface of a liquid. This is the point number 2, and here we are just assuming the height of a liquid is the y2, and rest of y2 minus y1 we can assume here the y2 minus y1 we have, that is called the h is there. Okay, so this is the one of the basic assumption. And here what kind of the energy associate with the liquid as it flowing through the orifice or the nozzle which we have made at a height of y1. So at the point 2 we have the potential energy. So potential energy we can write here, that is called the rho g and y2. Okay, so here we are also assuming the some basic assumptions of the Bernoulli principle, that liquid is a incompressible, that means throughout the volume the density is the same. So as I am just making the concept of the potential energy. Now what is the kinetic energy? Now it is one of the basic assumption, another, that we are using the concept of the equation of continuity. So here we are just assuming that a2 a2 v2, that is equal to the a1 v1, and here we are just assuming the a2 upon a1, that is equal to the v1 upon v2, and here we are just making the one of the assumptions to proving this Torricelli law, that a2 is quite greater than compared to the a1. This is the portion that is having the area, that is called the a1 is there, and this is the quite smaller as compared to the area that is called at the point 2, that is called a2. And as we are just making this one assumption, so we are just getting that v1 greater than v2 compare. Okay, so here we are just assuming the velocity of a liquid is the 0, and here we have the velocity of the liquid, that is called the v1. So here we have the kinetic energy which is not available as per the assumption, that is called the 0 we have. Okay, now the container is not openable to the atmosphere, so here we are just assuming the pressure, that is p2, that is called the absolute pressure p we have. Okay, we have assumed, and here we have the nozzle which is open to the atmosphere, so we are just assuming that p1 is equal to p atmospheric is there. Okay, so here we are all the time we are just using the basic conceptual portions of the Bernoulli theorem to be keep in our mind. Now what kind of the statement and the, that mean, formula construction on behalf of this concept we will find out here. So here we have the general statement. Efflux means the outflow of liquid, and according to this law, the velocity of liquid is equal to the velocity of freely falling body under gravity, as P is equal to PA through the orifice. Okay, so how can we prove it? So we will apply the Bernoulli principle at the point 1 and point 2, and at the point 2 we have the potential energy, kinetic energy, we have the 0 as per the notification of the equation of continuity. Pressure is, that is called the container pressure we have, that is P2 is equal to P, and at the point 1 we have the total energy, that is called the potential energy, kinetic energy, as well as the pressure energy is there. Okay, so here we are just assuming important assumption we have. Assumptions already we have made. Further I am just writing it. A2 V2, that is called the A1 V1, as we are just getting the A2 upon A1, that is called the V1 upon V2. So this implies, as per our assumption, A2 is greater than A1. So the surface is very large, so we are just assuming, or it seems to be that water is stable is there. So V1 greater than V2 कि पानी यहाँ इस पॉइंट के ऊपर रेस्ट में एज्यूम किया गया है. सो इस केस के लिए हम यहाँ पर एक बेसिक एज्यूमशंस कर लेते हैं. ठीक है. नाउ अप्लाई द बर्नौली प्रिंसिपल. Energy at 2 is equal to at 1. So what are the types of the energies we have? So first I am just making the assumption of the pressure energy is there. So as I am just writing absolute pressure we have, that is called the pressure energy at the 2. Now the potential energy we have, that is called the rho g and y2. As kinetic energy we have already assumed that kinetic energy is a 0, because we are just assuming the v2 is equal to 0, that is equal to the pressure energy, that is called the PA is there, plus potential energy, that is called the rho g y1, plus kinetic energy is equal to half rho v1 square. Okay, so this is the basic principle we have used. Either in the either part the particular energy is not there, so we are just eliminating it. Okay, so now we are just solving it and finding the concept of the v1 is here. Now here I am just making the simpler calculation regarding to the V1, as I am just keeping P minus PA plus rho G Y2 minus Y1 and rho by 2. I am just separating, so I am just getting this one scenario of the formula that V1 can be straight under root of 2P minus PA upon rho, and the 2GH is there. Okay, now here I am made the substitution that Y2 minus Y1 can be straight in the part of H is there, which already I have mentioned in the diagram. Now V1 is coming in the part of, that is called the 2P minus PA upon rho plus 2GH is there. Okay, so this is the simplest part we have in the sense of the velocity. Now cases are here, as we are just assuming first case that P is greater than PA, that means container pressure is too much greater compared to the atmospheric pressure, so we can hold the velocity of the liquid through the orifice by the container pressure. So here we are just assuming, and we can neglect the term 2GH can be neglected. So the formula comes in the portion of that 2P minus PA is to be divided by rho we have. Okay, the velocity through the orifice can be controlled by the container pressure. Now the second portion, which belongs to the Torricelli law of efflux. Now we are just opening the top of the container. Okay. Now tank is open. So whenever we are just opening the face of a tank, okay, to the atmosphere, so we are just assuming that P is equal to PA. So whenever we are just keeping this value in the portion of P is equal to PA, so we are just getting V is equal to under root of 2GH. So this is the possible result of the Torricelli law of efflux we have, and at this time we can understood the term that the velocity or the outflow of a liquid through the orifice, which is equal to the velocity as this one is a outflow of a liquid we have. So the velocity of the outflow of a liquid is equal to the under root 2GH, and which is same as it is the velocity of a free falling body towards the surface of the earth under the action of gravity. So this is the result of the Torricelli law of efflux we have.